performance or reduce the physical demands. Hence, they are designed to address a number of functions. An overview of their utilization and design will be presented by a panelist, by a set of experts. So first, Professor Sterling from the University of Michigan will introduce the different types of exoskeleton and their fit. Then Professor Srinivasan from Clemson University will present the challenges posed by passive exoskeleton in industrial applications, and Professor Ferris from the University of Florida will discuss the delicate control of active exoskeleton. Then Dr. Wisniewski, head of Human Factors and Ergonomics Unit at the Federal Institute of Occupational Safety and Health in Dortmund, Germany, will discuss health and safety issues in relation to the use of exoskeleton. And Dr. Monica from the Italian Worker Compensation Authority will present the perspective of an insurance system. And last but not least, Dr. Bartenbach, for the CEO and founder of Oxivo Switzerland, will present the challenges of a designer. This presentation will be followed by a panel discussion. And so if you have any questions, please post them in the chat. And Dr. Graf, who is our host today from the IEA, who is the Vice President, Secretary General, will consolidate this question, and time permitting, they will be answered by the by the panelists. So the first presentation is going to be by Professor Sterling. So please, Leah, go ahead.
Can everyone hear me okay?
Yes.
Perfect. And we're seeing my screen?
Yes.
Excellent. So in this talk, I'm going to show pictures of exoskeletons, and my selection of exoskeleton examples are not an endorsement for a specific company. So there are different roles that an exoskeleton can take. An exoskeleton can augment the human's capabilities. For example, it can enable you to lift more weight than you usually could, or run faster, or for a longer time. An exoskeleton can also assist the human's capabilities. In this role, a person doesn't do more than they could without the exoskeleton system, but the exoskeleton offloads some of the effort required to potentially reduce musculoskeletal injury risk. An exoskeleton can also support rehabilitation. For this goal, the desire is to increase capability over time based on limitations in motor abilities, which may be due to an injury, a disease, or a surgery. There are two primary types of exoskeletons, although systems may have components from both categories. Exoskeletons can be passive and have supportive structure only. They can also be active, where motors or a form of actuation are present that can move the underlying body segment. These active systems have controllers, which define the rules for how the motors respond. These rules can be fixed, that is, the rules stay the same, or the rules can be adaptive. This means that the rules change as the exoskeleton learns about the user or the task. The images shown highlight different types of exoskeletons that are commercially available and the goals of these particular systems. These examples highlight a few use cases for why we may want exoskeletons. In our other talks today, you're going to hear more about exoskeletons for industry and medical and other applications. The efficacy of an exoskeleton for supporting the design goals is affected by how a person moves with and uses the exoskeleton. This fluency between the human and exoskeleton is affected by three fit characteristics, and I'm going to talk a little bit about each of these in more detail. So static fit considers the anthropometric characteristics of a user, as well as the sizing of equipment components. This fit characteristic is relevant for exoskeletons that require kinematic alignment with user body segments in order to enable comfort and to prevent injury due to inappropriate application of forces and static postures. So for example, the Lockheed Martin Onyx system shown on the left, the motor needs to align with the knee axis. Whereas the Myomo system shown on the right, the motor needs to align with the elbow axis. Misaligning an actuating component can create undesired forces and moments applied to the person, which can increase risk. When evaluating static fit, it's important to consider the relevant postures to appropriately assess alignment for the desired tasks. Different use cases will have activities that consist of a variety of tasks, and it's important that the exoskeletons be evaluated for the relevant task-specific postures. When determining the necessary adjustability of an exoskeleton, it's important to consider a multivariate approach to anthropometric dimensions, where you evaluate different combinations of the underlying anthropometric measures. People all have different shapes and sizes, and this can influence what workers may fit into a particular device. There's also a subjectiveness to comfort, which can lead to a different desired static fit across users. Each exoskeleton system will need to consider how varying size affects their specific performance requirements, as well as what people can then statically fit in these systems. And here so far, I've discussed the fit between the person and the exoskeleton, but there's also a static fit with respect to the environment. The exoskeleton will change the person's body dimensions, which may affect their ability to perform their job. For example, going into a car on an assembly line or fitting in a manhole as a construction worker. This measure of fit is important, but it's limited. Just because a system has good static fit does not mean the system will enable a dynamic fit throughout motions. Dynamic fit considers motion and task-specific performance. This characteristic is relevant as exoskeletons should minimize restrictions on mobility and minimize internal human system opposing forces, and this will enable operational tasks to be performed. When the kinematics of the human exoskeleton are misaligned, forces exerted by the operator are countered by forces internal to the human exoskeleton rather than being transmitted to the environment. And this inappropriate coupling creates inefficiency, it can increase fatigue and metabolic cost, and it can lead to injury. So the goal is for the wearer to perform the operational tasks they need. Here I'm highlighting two examples of functional task assessments that can be used to assess exoskeletons. For example, the Army uses representative obstacles to examine task performance, while the National Institute of Standards and Technology has developed a platform for examining exoskeletons used in industry for tool handling tasks. Functional task assessment is one method for assessing dynamic fit and can be as simple as a binary yes/no for task completion. It can also be as detailed as using wearable sensors to quantify characteristics of performance, such as coordination, agility, or balance. When considering dynamic fit from an experimental perspective, it's important to consider the bias due to the participants and the tasks that are selected. Users should be selected that are representative of the actual population expected in a workplace. Similarly, tasks must be selected that are representative of the use cases. So during different phases of development, these tasks may be simplified. However, with system maturity, these tasks must be appropriately expanded. Exoskeletons may not be appropriate for all tasks, so an assessment needs to be made for which tasks the exoskeleton is appropriate for. And a decision must be made if the exoskeleton is worn all the time or only for certain tasks and people. Dynamic fit provides an opportunity to consider mobility of the human with the exoskeleton, but it does not guarantee that the user can efficiently move. A motion that is feasible to achieve may not be natural, and delays in active support can lead to attention being focused on the act of moving rather than the operational task. Cognitive fit considers this perception, cognition, action process. This characteristic is relevant to exoskeleton fit as the operator's cognitive capability must be maintained such that operational tasks, including decision-making, can be adequately performed. So here I'm showing a simplified human information processing model that includes 4 phases: sensory processing, perception, decision-making, and response selection. Sensation includes touch and proprioception, which is the awareness of one's body orientation and posture. Executive function combines the perception and decision-making boxes and includes cognitive functions like memory, the ability to direct your attention, the ability to encourage action, and mental models, which are our dynamic representations of systems in our environment. Response selection includes our motor actions. So our motors can be autonomous in that we don't think about the motions we perform, or they can be conscious in that we actively move our body. These cognitive stages are connected. Sensory processing and executive function will both affect response selection, and the responses we select then affect the following sensations and decisions made. So the question becomes, how does wearing an exoskeleton affect your sensation, your directed attention, or even your motor selection? Different task goals that we have may lead individuals to prioritize different aspects of gait. While some exoskeleton studies look at metabolic rate or muscle activation as a measure of energy expenditure, there are additional motion priorities that people will have when using these systems in an operational environment. For example, there are influences on our movement related to comfort and balance. And when we think about using exoskeletons to perform tasks, there's also an influence on the performance time, along with the task accuracy and precision that we need for that specific job. So when evaluating exoskeletons, it's important to consider how these priorities may influence our system usage. So when considering cognitive fit, we need to determine the relevant mechanisms to assess based on the operational environment. Directed attention and agility may be relevant for military applications, while perception and coordination may be of more importance in a medical application. The simplified human information processing model highlights the flow of information, but there's variation in people that may yield different mechanisms to drive their individual behavior. For example, if a person has a lower threshold for perceiving a force or a velocity, they may respond in a different way to an exoskeleton. Studies have shown this variability in how adept people are at using exoskeletons, and these could be reasons why there is this variation. Another reason why users may respond differently with an exoskeleton is because they're not appropriately trained on how to use the system or how the system should behave. Training can support appropriate mental models and then the usage of the system. While static and dynamic fit can be assessed at a particular point in time, cognitive fit can evolve as the user adapts to the system. Understanding the cognitive mechanisms that drive adaptation and adeptness is ongoing research. In today's talk, I introduced types of exoskeletons and highlighted 3 characteristics of fit. Changes in motor strategy may arise from static or dynamic fit of the exoskeleton, but can also arise due to the cognitive fit. A design and evaluation approach that considers the diversity among us will benefit exoskeleton design, as well as integration efforts. As our motion priorities influence system usage, it will be essential for us to consider these priorities in the context of exoskeletons deployed into different application areas. Thank you for your time, and I'd now like to hand off the presentation to our next speaker.
Thank you, Professor Sterling. And now, Professor Srinivasan, please, you have the floor.
Thank you, Bernard, and good morning or good afternoon, everybody. I'll jump straight in. Thank you, Leah, for setting the stage for the things I want to say very nicely. Today, I want to start with a little bit on what we're doing with exoskeletons in the industrial space. So if we had a crystal ball to look into the future, we are at a point where Industry 4.0 is turning into Industry 5.0 and realizing that everything is not going to be automated. Industry 5.0 puts humans back into industrial production. So even as research on robotics and automation is progressing on one hand, industries are currently facing the challenges of labor and skill shortages, and as well as an aging workforce. And these challenges are further exacerbated by the problem of occupational injuries that threaten to further impact productivity and revenues. So given this context, a worker staying productive and healthy and safe and actually being skilled as well very much still defines the focus of the future of work. So what are exoskeletons? Bernard gave a very brief introduction and then Leah continued on that. So I don't want to really go into this too much. I just wanted to draw your attention to 2 things here in this slide. We're not talking about autonomous robots that would replace a human. We're also not talking about prosthetics that would replace a specific body part. We're talking about wearable systems that would work with a user to augment or reinforce or even restore their performance. In the context of industrial work, the use of exoskeletons can help make physically demanding work more accessible to more people. So if you think about females or older workers, those with disabilities, people that you wouldn't expect to stay in physically demanding work, that conversation can change as exoskeletons get introduced, and that's sort of the potential we are faced with today. Our research program in this domain mainly focuses on 3 different kinds of questions. The first, of course, is do they work, right? Do exoskeletons work? If they do, what are the right metrics to even decide whether they work? Are we talking kinematics? Are we talking energy expenditure, people's perceptions, performance, etc.? So that's one bucket of research. This is critical to help with iterative device design. But even when you consider industry adoption, creating the evidence base for what exoskeletons work and how and when and where is kind of the logic there. From there, we move on to determining what are these use cases. If you were an industrial consumer trying to understand whether exos fitted your industry, what tasks should you be thinking about applying exoskeletons to? And if you think about the passive exo space, shoulder, or rather more generally, arm support exoskeletons and back support exoskeletons are the 2 kinds that are becoming very popular and are getting commonly applied. So now that there are several designs available, even within those categories, once you decide on use cases, how do you go about selecting which exoskeleton best matches the tasks that you want to apply them to? That's sort of the second bucket of work. And the last is an exoskeleton could work perfectly theoretically in the lab, and that's not same as the field. So what do workers and stakeholders in management think about exoskeletons? Who wants them and why? And what are some of the opportunities as well as concerns that people might have or we should be aware of as researchers and practitioners as we go about applying these exoskeletons? We broadly ask these questions in the context of manufacturing work, construction work, and are just stepping into some work in healthcare. I'll touch upon a little bit about fundamental lab studies that look at quantifying effectiveness of different exoskeletons, some of which are even commercially available, and transition into talking about field adoption and the factors that emerge there. So this is a sort of quick recap of a series of studies we ran on comparing the biomechanical effects of different back support exoskeleton designs. The two exoskeletons we tested here were both passive, and they're both commercially available. One of them is the BackX, and the other is the Levo device. This was an older version of the device, version 2.5. And the reason we compared these devices were that one device weighs and costs about half the other, and both of them incorporate passive torque generation mechanisms about the hip that are intended to augment your trunk extensor muscles, and yet they have distinct design features. So the BackX, for instance, includes a structural frame that pulls your torso backwards by distributing the pressure to the shoulder straps and the chest pad, but the Levo transfers the load through pushing against the chest only. And support levels and assistance modes can also be adjusted differently in the 2 devices. So what did our people do as they were wearing them? They were performing precision assembly tasks. They were doing them at different heights from the floor, at different distances from the body, and they were also doing it with their body orientation being either symmetric along the sagittal plane or as they had to twist their trunks more and more. And I want to show you a quick snapshot of what we found in terms of trunk extensor muscle activity levels. So to interpret this figure, here is a person standing. The feet location shows how they were standing, and this is along their mid-sagittal plane when they are not twisting their trunk at all. And you're seeing our results for muscle activity organized by height from the floor. This was a specific use case where we even looked at some heights below floor level, but in general, you're seeing ankle height, knee height, and waist height. And here you're seeing people going out farther and farther away from their body. And while this was symmetric or no trunk twisting, you're seeing people, what happens when people twist their trunk by 45 degrees and further twist by 90 degrees. The EMG results presented here are comparisons to how people's muscle activities were when they were not wearing exoskeletons to perform the same tasks. So if the muscle activity reduced on wearing the exo shown here, the BackX model AC, then the green, the level of green shows you to what extent it reduced, and red meant that the exo muscle activity actually was greater than the no exo muscle activity. As you can see here, broadly, both exoskeletons were effective, but the extent to which they were effective varied based on what specific tasks people were doing, in the sense that the height of the target locations and the distances from their body and whether they had to twist their trunk or not changed a lot about what we're looking into. The reason we ran a study like this was if an industrial end user was thinking about how do you configure tasks when somebody is wearing an exoskeleton, even though they might be staying stooped or bent for a long time, we wanted to show that the height at which the exo would be effective and the whether symmetric or asymmetric postures would affect it was needed to be considered. And this is one example of that. We also considered similarly repetitive lifting tasks involving exo use. And again, there's 3 different levels shown here. No BSE, meaning no back support exoskeleton, using the label, the same device as in the previous slide versus the back X. So here is a snapshot of what their metabolic energy expenditures looked like when they were doing repetitive lifting from the ground level, from the load being placed at the knee level, both in the symmetric conditions or along the sagittal plane versus an asymmetric condition. And we observed that the passive back exos could reduce metabolic energy expenditure as well, generally in the 10 to 15% range, as long as the loads were symmetric. But as soon as asymmetric trunk twisting came about, you couldn't see those beneficial effects anymore. So summarizing the previous 2 slides, the short answer would be yes, exoskeletons work, but you need to be aware of what specific task you're considering. And then between choosing different exoskeletons, again, there are design trade-offs that one needs to be considering. So this was just looking into the beneficial effects of exoskeletons from a very biomechanical and ergonomic standpoint. We do similar work in asking, are there any unintended effects of exoskeletons while they work when you are doing repetitive lifting or when you are staying at trunk bent postures for static exertions? Is there anything else to consider? And this is an example of a study where we looked into what happens when you walk wearing these exoskeletons. And we first did some work to quantify the torque profile of the passive exoskeleton itself, and then use that. And the major findings were that because the exoskeletons are generating assistive hip extension torques as a person is using them for these specific industrial tasks, the same hip extension torques happen to also impede hip flexion and increasing the mechanical energy for swing forward when you're applying them to gait. So the idea here is that if you were an industrial user wearing an exoskeleton, it's not like you're going to stand in one place and only bend and not do anything else, right? So even if you were to walk about your workplace, we wanted to ask, is there anything that you should be thinking about? So there were some small changes on hip range of motion and hip flexion velocity. But then when we looked at what those changes did to the hip and knee power that was needed while walking, we didn't see drastic effects among males, but among females in our study, there was like a 1/5 increase in energy expenditure, or we could consider that this would increase energy expenditure based on the relationship between hip power and energy expenditure. But my point is that it isn't as straightforward to say that it can help this. And then there's not only one thing a person is doing in actual field settings. So considering this in a more nuanced way would be something that we should be doing. So that was a very brief snapshot into some of our basic lab studies on what happens with different designs. We stepped out into the real world and said, what factors determine a person's readiness to use exoskeletons in the context of construction? These are some of our responses from their open-ended interview questions, and we organized them into benefits and barriers and so on. So what did we see? People were generally excited about exoskeletons. They were more excited before they got to saw the real exoskeletons we were talking about. So we did a little show and tell, showed them what the exos looked like and what they could do, allowed them to wear the devices and experience them for a bit before they answered our questions. And in terms of expected benefits, it was great to see that everybody expected a reduction in musculoskeletal disorders and injuries. And some among the management even thought that that would help with their worker retention. So they were equally excited. The one thing for us that surprised us a little bit was that people were associating even these passive exoskeletons with productivity gain. And that isn't always the case, but we know that. But that was just something that we discovered while we talked to the folks. People were, of course, thinking about the financial gain, both the cost benefits and the ROIs. In terms of the device itself, the usability of the device, of course, became really important. And comfort and fit, like Leah talked about, were chief concerns that emerged. And in the work context, people were concerned if the EXO would sort of impede their compatibility with the other PPE that they must be wearing and using. There were some safety concerns that came up, given the way the device is projected out of your body. Were there any additional catch and snag risks in an industrial setting? Were there any hygiene issues or any allergic reactions people needed to be aware of? And some workers, or not just workers, even stakeholders wondered, would the devices be giving our workers some false sense of security because of which they might think it's okay to do certain things that safety professionals have been trying to train workers out of thinking that it's okay to do. So there were very valid and interesting concerns that emerged. And then in addition to that, we used their responses to all the questions we asked them and said, if we were to construct some kind of a decision tree about what factors would help predict somebody's willingness to use an exoskeleton, this is also in a construction context, some of the questions that emerged as the key factors that were differentiators in responses were, the first was, will exos help improve your productivity? And the scale, they answered on a Likert scale ranging from 1 to 5, where 1 was definitely yes and 5 was absolutely not. And you see that the 5, the absolutely nots, separated out. There were a small number, 6 out of over 300 people that said that. And clearly among them, there was an 80% chance of them never using an exoskeleton. They said, no, we'd not use an exoskeleton. Among everybody else, the second branch was, is your work physically fatiguing? And those that said 1 had like, yes, my work is physically fatiguing, had a very high probability of saying, yes, I'd be willing to use an exoskeleton for my work. And the other responses, nobody said 5, this is construction work. The other 2, 3, 4 responses came together. But the next branch, interestingly, in the construction setting was, do you work on a roof? And the roofers basically branched out into having different responses from people that said maybe sometimes versus no. And that's sort of the preliminary results from trying to understand among 70 odd questions that people answered in a survey, can we predict their initial willingness as they enter right into the exoskeleton trials? Are they going to be willing to wear an exo or not? I know that I've run out of my time, so I'm going to stop here and just leave you with some of the big questions we have in the field. I don't need to say much. And Bernard, if you'll allow me to keep the slide on for 10 seconds, I am done. And I'd like to pass it on to the next speaker.
Thank you, Divya. The next speaker is Professor Ferris. Please, Dan, you have the floor. Dan, you are muted.
Yep, I am sharing the screen now. You should be able to see it, and you should be able to hear me. Well, good.
Yes. Yeah.
Okay, so I want to talk about how do we get to the next generation of active exoskeletons that are more successful than what we have now. And really, in my view, the limiting factor is control. There are an awful lot of devices out there, and this is just a selection of some of them. All the ones on the top row are designed to help individuals that are physically intact and healthy, and the ones on the bottom are designed for individuals with neurological or musculoskeletal issues. And there are different control concerns and issues to deal with for the 2 different types. But the reality is we can build the hardware right now. It's not as lightweight and not as powerful as we would really like, but we can build the hardware. And right now, the biggest issue we have is control. How do we integrate the exoskeleton device and the actuators so that they move fluidly with the human? When we think about the different strategies, if I try to group them into different categories, the most dominant control approach has been really a state-based control with intrinsic sensing for active devices. What this basically means is they put either kinematic or kinetic sensors on the exoskeleton to either measure forces between the human and the exoskeleton, or they measure accelerations or velocities or positions of either the human limbs or the exoskeleton. They take that information and try to calculate what the human intent is and then move along with it. This approach actually works fairly well when you have a rhythmic cyclical task where the last few movements are very similar to the next motion, because you can see what the intent of the human is in terms of the motion, and then you can try to reproduce it. So if you're walking at steady state speed on a flat level surface, it actually, the success is quite high. It becomes a little bit more difficult when you're doing acyclical activities, some discrete motions of the upper limb, or you're trying to deal with, react to the environment. Imagine moving through a crowded subway where you're stepping around people and each step is really different from the next step. Another alternative is to incorporate some sort of muscle activation pattern from the individual. This could be with electromyography. Some people are actually thinking myomyography, or a few other ways, but basically getting intent out of the muscle activation to use it as an input to the system. There have also been, especially for individuals with disabilities, looks into using electroencephalography or EEG for a lot of patient populations that have distal weakness in the muscles and their neural signals, think spinal cord injury or stroke. Trying to rely on muscle signals may be very problematic. And if you can't get good, reliable motions out of the individual, then you need to find another source. And right now, a lot of places are trying non-invasive electroencephalography. Then there's always cortical implants. Can we actually do a surgery and implant a computer chip into the motor cortex or the posterior parietal cortex and use that to get some signals out of the brain and use it as a feed-forward signal for the exoskeleton? And in reality, you know, if I were to look forward 10, 15 years in the future, my prediction would really be that we're going to use some hybrid control. We're going to use variations of some of these 4 different categories up above. One of the biggest things to fight right now is lag. A lot of exoskeletons, when you put them on and try to move around, you almost feel like you're walking through water or molasses, in that you make the motion and the exoskeleton has to catch up. And that is a difficult thing to overcome. And I think in the future, if we basically try to use all the information we have available, we're going to have more success for the controllers. How do you evaluate these? Human experiments take a lot of time and effort, but in reality, they're really the best way to determine whether this is going to work. We in our lab are actually working on robotic phantoms that can do cyclical motions that you can put the exoskeleton on, so that you can try to examine the control issues without having to get to the human subject's standpoint. But in the end, we're going to have to do human experiments. And so what are you going to measure? And Dr. Sterling mentioned this a little bit, but you have to measure a lot of different parameters to figure out the success of the exoskeleton. So let's imagine we have our human, we have some robotic intervention of putting the exoskeleton on. We can measure their oxygen consumption or their carbon dioxide production to measure metabolic cost. We can film them to get their kinematics, so we can put IMU sensors on to get kinematics. We can have them walk on force class platforms to measure ground reaction forces, or you can use insole pressure transducers to get the same information in the vertical direction. You can put electromyography, EMG sensors on to figure out muscle activity. You can actually stimulate reflexes and actually measure reflex modulation to see how they're adapting. And you can put electrodes on their head while they're walking around and moving and using the devices and actually measure brain dynamics. All of these are feasible, and there's large literature examining use of different exoskeletons with these types of devices. This is what a normal data collection looks like in the lab while you have an exoskeleton on and you're trying to measure a range of different parameters. In this particular instance, we're having subjects walk up on an incline on a treadmill while we measure energy production. And a key aspect of getting these devices out in the field really is going to be testing them in the field, not just in the laboratory. There you have to contend with things like changes in terrain, changes in interactions with other individuals, a change in the relative variability in the motion patterns. And I think getting out in the field is really key to evaluating the device for the future. An important aspect that's really it's fundamental to getting a good controller for an exoskeleton is sort of understanding the way that humans currently use their nervous system for control. When you want to do a certain task, like pick up a cup, you have this desired movement in your brain. You then use a part of your brain, which we call an inverse model, to sort of say, here's the motion, how do I send electrical signals to my muscles to make it happen? That electrical signal goes to the muscles, you produce the motion sends sensory feedback. At the same time, you have the commands that you're generating in your brain. You send a copy of that signal, what we call an efference copy, to another part of your brain that plays a forward model in your brain, forward, so that you can predict what type of sensory information you're expecting. And so when you take the actual sensory feedback with the predicted sensory feedback, you can then determine where there are errors in your control system and how you're moving and adjust it appropriately. There's some really nice experiments by Daniel Wolport, who has looked at what happens if you play around with human-machine interactions by delaying the robot assistance to you. And what he found out is, if you get even as little as 100 milliseconds, you start getting a change in how your brain is perceiving that assistance. And when you get up to 200 or 250 milliseconds, actually you no longer perceive it as part of your motion, and it's some external agent that's doing it to you. So reducing this lag time in the control is super important for future devices. Historically, a lot of exoskeletons have been judged primarily on their biomechanics, on their energetics, and measuring the control dynamics. But I would actually argue that we really need to take into account two other parameters, and that is the agility of the individual using the exoskeleton, and also the embodiment that the individual feels while using it. In an ideal world, you put on an exoskeleton and it feels just like a normal part of your body, and you don't feel different with it. On the other hand, if you're putting it on and it feels like this external perturbation to your system that you have to contend with, it becomes almost like a tool. It's like picking up a hammer. And yes, you can use it, but you're going to have a different success rate in terms of adapting it into your body schema. In our laboratory, one of the breakthroughs that we've had is really trying to work with companies, whether they be a big national corporation, international corporation, or a small startup. They are focusing on the hardware in a way that one lab cannot do both the hardware and the controls and get it robust in the field at the same time. So this is an example of one of the experiments we have ongoing. Rachel Heibart's a PhD student of mine working on different controllers. In this particular instance, we're using proportional myoelectric control on a DeFi ankle exoskeleton. And I would encourage people, companies and research laboratories to try to develop collaborations where they can figure out the best ways to optimize the control with field-ready exoskeletons that are already in development. Lastly, I just want to thank all of the researchers in the lab that have helped out with this. We've had a great crew of exoskeleton researchers over the last 20 years, and I'm happy to answer questions.
Thank you, Professor Ferris. And now we're going to have Dr. Wisniewski presenting on the health issues.
Okay, just a quick check. Bernard, can you
Yes.
see my slides and hear me?
Perfect.
Okay, thank you very much. Yes, so hi everybody. I would like to use the next 10 minutes to give you an occupational safety and health perspective on exoskeletons. And by that, I mean mostly passive systems. So basically, yeah, the systems we see currently out there on the market that you can buy and use in your company. Also with my fellow speakers, what they have shown already from the systems and the pictures. So I don't show you any more pictures since we already have set the scene properly. Okay, so on the next slide. So here we go. First of all, I would like to talk quickly and briefly about working conditions in Europe, because of course, exoskeletons are there to support the musculoskeletal system. And so I would like to talk briefly about physical working conditions in Europe. And I brought you some data here from Eurofound. And basically the question they had here was, does your work involve carrying or moving heavy loads? So for some of the passive exoskeleton, a possible field of application for the lower back. And there you can see that in Europe, in the European Union, about 30% say, well, that happens at least 25% of my time. So this is, I would say, a quite common working condition we see out there. We had another question, or there was another question in this survey on, does your work involve tiring positions, awkward working positions? So this is maybe more the target area for upper body exoskeletons. And here, this the graphic is a little difficult to read, but here we can see that 50% say, or 60% almost never, but the rest says, well, either this is between 25% and 75% of my working time, or this is all the time. So basically, I think what we can see from these two slides, there are physically challenging working conditions that we see out there in Europe. So the next question would be, since exoskeletons are an emerging technology, which are not available for such a long time on the market, how do companies cope with these challenges so far? And what we see here, that around about 80% of the companies say, well, if people have to move loads or do physical heavy work, we try to provide proper equipment to help them lifting these things. Furthermore, if you have these awkward postures, static postures, including prolonged sitting, we provide regular breaks. So that's what 60% of the companies in Europe say in average. These are the kind of measures they take if they face challenging physical working conditions. And the last slide in this field is if you have repetitive movements and physical strain, also what they try to do is to do rotation of tasks as a standard measure of ergonomic work system design. As you can see from these measures, they're very closely linked to the so-called hierarchy of controls. I brought to you here from NIOSH, because basically if you identify a risk at the workplace, you have different options to cope with this kind of risk. And as you can see here, we go from the most effective to the least effective, starting with the elimination and remove the hazard, replace the hazard. And well, this is often not possible. And then we talk about isolating people from the hazard and changing the way people work. And only, I would say, as the last line of defense, we protect the worker with personal protective equipment if everything else fails. And Divya already had that question on her last slide, stating what are exoskeletons? Because we put them close to the human body. Is it PPE? Is it not PPE? Will be interesting later in the discussion to also get to know the opinion from the audience. Also, I think I saw it on the chat or the Q&A, what kind of tasks or when do I use these kind of exoskeletons at work? And if we still have in mind the hierarchy of controls, I would say, well, if you do not have a chance to use a tool that does not need to be attached to the human body, like a lifting support device, then you might consider that. If there's no chance of rearranging the work, to make it a less physical demanding task. So basically, if you do overhead work and there's any chance to get the working piece lower below your heart level, that's the way of doing it, maybe before using an exoskeleton. Also, and that is closely linked to the other two bullet points, the task, if the task is mobile, if you don't have a fixed workstation and do not have repetitive work. Because if you have that, then, well, you should really consider, is there another tool I can implement to well, help with the challenging task. So how do we get along with that in Europe, and here also specifically in Germany? And I brought you a guideline by the Association of the Scientific Medical Societies, and there was an extensive review done on the use of exoskeletons in the occupational context for primary, secondary, and tertiary prevention of work-related musculoskeletal complaints. Also here you see all the publications which are available in the field. And I didn't bring you the whole document because it's really a lot of information there, but I wanted to share the key messages, especially on the primary prevention. As I said, this was done by an extensive literature review, which is documented. And in the end, there was an expert workshop to see if there's a consensus on the different guidelines and messages, key messages that you can see here. And well, the first one I already showed you, we have to follow the hierarchy of controls when you implement and when you want to implement exoskeletons. A preventive effect of exoskeletons on musculoskeletal complaints or even disorders cannot be substantiated on the basis of current scientific knowledge and experience from professional practice. So I'm putting really a little water into the wine, I think, with this sentence. I mean, it's an emerging technology, but currently, I think that's also a question from the chat, we don't have information on long-term effects. We have lab studies, we have very few emerging studies on long-term effects, but the majority, we really cannot tell what's the effect if you use it every day at your workplace. We are still collecting this kind of information. Now we switch from the key message to key recommendations. For workplaces where exoskeletons are used, a specific risk assessment should be carried out with reference to the exoskeleton used. Because of course, on the one hand, you use the exoskeleton to improve the work. On the other hand, you have to consider I'm wearing something on my back, mostly on your back, lower back, upper back, and you have to see, well, does it impose any further risk? I brought you an example from our German social accident insurance company, where you have a draft and all different risk categories, also a document you can download, I think, with valuable information. Also, as long as a health benefit from the use of exoskeletons in occupational activities is not supported by scientific evidence, the use of an exoskeleton should be voluntary for employees. So if we don't know that for sure, should be voluntary. And finally, well, this is closely linked, this recommendation, because since we just don't know everything yet, the use of exoskeletons should be monitored medically and technically by occupational health and safety practitioners in the company. Especially the physician in charge is a person to involve if you implement this kind of technology. Moving to the last part, risk assessment. This is here the guideline that we do have here in Germany, and it's about the hazards that may arise during the use of an exoskeleton. Also here, again, a recommendation where you see as a general rule, an exoskeleton may not be used as a measure for reduction or elimination of hazard unless the exoskeleton is used as personal protective equipment. I brought you one example of, and this is how the whole document looks like. You have the possible hazards on the left side, and also here linked to the former presentations. For example, you have the aspect of mental stress. So if you use that in your company, there might be a lack of acceptance. We also heard that in the presentations already. It might be difficult for the employees when they are forced to use the exoskeleton. There might be group pressure. So, and then you can see what are possible measures to do there. You can do a risk evaluation, and you can also then see, is there a need for action? And we have that in this document. There is, I think there are 12 categories of different hazards to use. I don't know if I have one more minute, because that might also answer another question that I've seen on the chat. It's not only about doing the risk assessment for you using the exoskeleton, but also how does the work change when I use an exoskeleton. So basically, I do an analysis of the workplace with the, I don't know, with the ruler or with the OVAS. And then I use an exoskeleton, but then is the score still valid? Is it the same score? What I can say there is well, there's work is done, but it's difficult because of course the different exoskeletons do have different impacts. And it's not that easy to say, okay, if you're using this kind of exoskeleton, we can reduce the points for lifting, I don't know, by 2 or something. So, but this is work that is done in the scientific community. So to sum it up, I would say we have still a high prevalence of challenging physical work conditions in Europe. We have an ongoing demand for human-centered work system design should be according to the hierarchy of controls. And exoskeletons are in this field an innovative approach as one future measure for work system designers, but still from lab or from field studies, long-term studies, little is known on risk and challenges, and therefore it should be closely monitored by experts. I hope I'm still in the time. Thank you very much for your kind attention. Looking for the discussion in the end.
Thank you, Dr. Wisniewski. Now we are asking our friend Dan Ferris to play the video to replace Luigi's intervention, as we had a technical problem. So thank you, Dan, for presenting that.
No worries. If it doesn't come through, let me know.
Thank you, Shane. And good afternoon, everyone, again. Now I'm sharing my presentation. But before start with the presentation, I introduce myself to clarify the reason of the present explanation. I'm Luigi Monica, and I'm a researcher of the Department of Technological Innovation and Safety Equipment of INAIL, the Italian Worker Compensation Authority. INAIL, as a research institute, develops specific activity to evaluate the implication of the new technological evolution on safety in a workplace. So, during the presentation, I will show some device and case studies application of occupational exoskeleton in a specific work activity as a result of a joint project between INAIL and Italian Institute of Technology. Generally, in Italy, we consider occupational exoskeleton as portable wearable service device used in the workplace which act on the body in a mechanical way, assisting the operator during a work activity. An exoskeleton modifies the internal and external force acting on the body and consequently the biomechanical load of the operator, with the intention of supporting him during a work activity through an assistive couple. For the description of the device and related case study presented, we used a classification of a recent article. So we have a classification on cinematic structure and classify the exoskeleton in rigid structure, anthropometric or non-anthropometric structure, and soft X-suite with no cinematic structure. Other classification is related on the type of actuation. So we have semi-active and active exoskeleton. The use of exoskeleton is not easy to implement in a workplace. For workers wearing occupational exoskeleton, in fact, several risk scenarios can be defined relating to their prolonged use. For example, new potential health risk could occur for the distribution of stress to other body regions. The use of exoskeleton affect motor control, gene stability, and alter the cinematic of the worker's body. Passive exoskeleton can potentially increase the activity of leg or arms muscle of the worker. The active exoskeleton have a high weight which can affect the health of the worker. An ergonomic issue related on the level of discomfort associated with wearing the exoskeleton are to address before using the occupational exoskeleton in the workplace. Furthermore, this device must be desirable to the end user. For this reason, in our project, we have used a human-centered design approach to involve the user, company, and worker directly in the exoskeleton design process. We can find the first of application of a human-centered design process to develop an occupational exoskeleton in a specific discussion paper carried out by IEA and published by European Agency for Safety and Health at Work. You can download the discussion paper using the link proposed on the slide. In the next slide, I present some video that show some different devices developed in a joint project INAIL and Italian Institute of Technology, are different occupational exoskeleton with different purpose. First, skull flexor, the occupational exoskeleton classified as past. We can see picture using occupational exoskeleton to be light code. The technology weakness level of the device is 8. It's semi-small and in the next slide, we present a video of other occupational exoskeleton called Exoshoulder. This exoskeleton is have a rigid structure, not anthropometric. For example, this device is useful to prevent work-related musculoskeletal disorder to the shoulder related to incongruous posture. The technology readiness level of this device is 5. The technology is validated in a relevant environment, so showing the video. The next slide, we can see other specific device called Exo-Elbow. This device is useful, for example, to prevent work-related musculoskeletal disorder to the elbow articulation related to repetitive tasks. Also, this device are developed in a joint project with the Italian Institute of Technology. And also, this device have a technology readiness level 5. Also, this technology is validated in a relevant environment. In the last video, we present Exotrunk. Is a specific occupational exoskeleton with rigid structure, anthropometric with active actuation. is useful, for example, to prevent work-related musculoskeletal disorder to the trunk related to lift and material handling. We can see in the video the experimentation of this device during the handling of luggage in the airport, and after experimentation in warehouse application lifting heavy loads. The technological weakness level of this device is 7. This system prototype is demonstration in operational environment, and in the next future, this device is put on the market, will be put on the market, and for the commercialization for its utilization in work environment. Yes, in conclusion, the exoskeletons can support worker in performing specific tasks in some work environment, and therefore can help prevent work-related musculoskeletal disorder. But there is little knowledge about this device and their real preventive effect on work-related musculoskeletal disorder, as some significant technical challenges and user acceptability issues must be addressed. In our project, the human-centered design approach has been very useful in exoskeleton design process to respond to real needs of the user and to solve some risk scenario related to their prolonged use. Thank you for the attention. I hope to be on time and clear in my explanation. I am available to answer a question that is necessary. Thank you, Chair.
Thank you, Dr. Monica, and thanks to Professor Ferris for playing the video. And now we'll have the last presentation, but not the least, by Dr. Bartenbach about the designer perspective.
Okay, can you hear me? I will share my screen.
Yes, we do.
Can you now see my screen?
Yes, perfect. Thank you.
Excellent. So, yes, yeah, thank you very much. Thank you for the invitation and for the interest, actually. So my name is Volker Bartenbach. I'm the CEO of the company Oxivo AG. We are actually an industrial exoskeleton company, a commercial exoskeleton company. And today I was invited here to show you a little bit about how we develop our exoskeletons to bring them actually to the market, and especially how we involve the end users in this development process to make sure that we actually develop something that is eventually also suitable. Before I get started with that, maybe a very brief introduction about our company itself. So what we do today at Oxivo, we are a spin-off from ETH Zurich. So this means that a lot of our activities today are based on the exoskeleton research that we did at ETH Zurich. In a transfer project, we then started moving away from basic research to more applied research and product development. And this eventually led to the incorporation of the company in 2019. And since then, we have managed to develop and bring to the market several exoskeletons that are now being used. So today we have 2 industrial exoskeletons on the market. This is our main offering. As a side offering, we have educational exoskeletons on the market to facilitate exoskeleton education, actually. But our main activities are really what you can see here on the right-hand side, industrial exoskeletons that are used by users across a variety of fields and use cases. And this is, today I thought about how I can show you how actually we invent or how actually we develop these exoskeletons together with the user. And I decided that I actually want to tell you the story of our very first exoskeleton that we developed, or we started developing some years ago, which is the Oxivo lift suit that you can see here on the left-hand side. You can see it is a very lightweight system, a passive system that has been developed and is designed to support the back and hip of users when they are lifting objects from the ground or when they are working in a forward-leaning position. And the development of the system, it started actually already quite some time ago, when I was still a PhD student at ETH myself. And back in the days, it was basically, we were in contact with a very large airport service provider. So basically the people who are offering the service of getting your luggage from the check-in counter into the airplane. And they were talking to us. They asked us, you know, at the airport, we have thousands of airport baggage agents, and their job is really to handle the luggage. They have to lift, they have to operate heavy suitcases every single day. During peak season, they handle more than 1,000 suitcases every single day. And in many cases, this is causing exhaustion, this is causing fatigue, and it can actually also lead to injuries. They also told us that they have been looking at a variety of existing solutions, but because of the dynamic environment, because of the dynamic nature of the work at the airport, they did not find anything suitable yet. And during their search for solutions, they also stumbled upon exoskeletons and thought, okay, hey, this is interesting. You know, this is a kind of a device that goes along with the worker, can support kind of anytime, anywhere. This is interesting. So they talked to us and they asked us, you guys, you are developing exoskeletons. So couldn't we find a solution that can support actually our baggage agents? And we kind of instantly said, yes, no, this is very interesting. This is a very interesting use case for us. So, but before we, of course, start developing, for us, it was very important that we understand what is actually going on. So in a very first step, it was very important for us that we understand the application. And this basically means we go to the airport, we observe all the different steps that are being conducted at the airport. We actually conducted the work ourselves for a certain period of time, just to really get a feel for the work. And it was important for us to understand what kind of movements are being executed during these tasks, what kind of loads are being handled during these tasks, but also kind of secondary factors like, is it conducted outside, is it conducted inside, do you have some kind of constraints, movement constraints, or in this example on the right-hand side, where the worker is doing the work on their knees actually inside of the airplane, and to really get an understanding about what are the environment, what are the movements that the exoskeleton eventually would need to provide support in. And the second step was then also to understand what is actually the problem. And this was very important for us to understand, you know, what kind of health issues or problems are arising from this kind of work. And of course, you have literature on that. You have statistical data available in at least in many fields. But in addition, it was always very important for us to actually talk to the people on site to get a first-hand, at least anecdotal feedback, what they say, you know, which body parts are fatigued in the evening. If you have been on the job for many years, did you have injuries? If so, how did they happen? Where did they happen? Because this, at the end of the day, for us was important to know which body parts basically our exoskeleton would need to reduce the workload on. And this was all, of course, before we actually started any kind of development at all. And before we started then the developing, it was important for us that we really define all the requirements that this kind of use case would put on our exoskeleton eventually. And the first part was basically what kind of support would be needed and what kind of body parts would need unloading. And at the airport, what we saw there, it was lifting loads of around 10 to 20 kilograms, so which is the typical check-in luggage there, during repetitive lifting tasks. And certainly we would need to provide back and ideally also hip support. And this was kind of straightforward, so I think we were not too much concerned about that part. But I think what was even more important for us to really understand what additional requirements come from this environment at the airport. And that became a little bit more complicated then, because it was very clear that they are looking for a solution that can be worn by the workers all day, for example. So it needs to be very comfortable and very easy to use. It was also very important for them that the exoskeleton can be used in confined spaces. You have seen the picture with the person in the airplane inside. So this means eventually the exoskeleton would need to be very small for them to not collide and cause damage all the time. Also, the work requires in this case that we can provide support while standing, but also while doing the kneeling lift task inside of the airplane. Another requirement was, for example, that the exoskeleton should not impose any kind of movement constraints, because sometimes at the airport, an airplane is coming towards you and you should be able to step aside or run away. And of course, you should also be able to do this with the exoskeleton connected to your body. Otherwise, it would be a health issue and a health risk for you. Also quite important at the airport was that you can wear the exoskeleton on top of your clothes, but also underneath certain clothes. And the reason for that was that at the airport, in many areas, a high visibility vest or high visibility jacket is mandatory. And this can, of course, not be blocked by the exoskeleton. Otherwise, it would again be a danger to our health risk. And last but not least, out of this, the requirement was that, yes, with this exoskeleton, our people need to be able to sit down in a car and drive around, because this is simply, airports are very big. And this is how they move between the individual airplanes to conduct their work, actually. And yeah, once we have this requirements list, then of course, our engineers can basically start. I think we have heard about this before in different talks. So there are certain exoskeleton design approaches, certain exoskeleton technologies around or available today. So we have heard about powered exoskeletons and passive exoskeletons. We have also heard about rigid designs and soft designs. And I think for us, it's not important which design we eventually choose. There is not a best design. I think there's only, or best technology. I think there's only a most suitable technology to enable us then to build exoskeletons that are suitable for a certain application or use case. And once we then eventually started actually developing, this typically looks a little bit like this. So we, of course, first start by sketching out ideas. We also start very quickly by building first prototypes. Exoskeletons, you need to feel them to understand what is working and what's not working. So this takes a little bit of time. This takes a little bit of trial and error. And we also talk to our partners in this phase already to understand if this is going into the right direction. And once we have then come up with a concept, with a design, and have built a first dedicated prototype, what was also very important for us that we then use the prototypes, went to the airport, let them test it, either on the job or in a more controlled environment for safety reasons, collect the feedback, and then iterate quickly. And sometimes iteration takes a little bit longer. Sometimes between these versions, there's only like a week or two. And over time, that we really make sure that we collect enough feedback and that we move the design towards something that they can actually eventually use in their given use case. And once we have achieved that, then of course we bring it to the market to see if this is what our customers eventually want. In the case of the lift suit, the result of this iteration process is again shown here. So you can see it's a very passive, a lightweight exoskeleton, basically connects to the upper body, to the lower body, and to the hip. In the back, you have elastic elements, elastic springs integrated. You can see here these blue elements. And what this system does, it's very small, it's very lightweight, so it's complying with all these requirements. And what the system does when you use it, when you lean forward, these elastic elements in the back basically store energy. This energy can be used to support your muscles when you're either lifting something from the ground or when you remain in this forward-leaning position. And of course, besides the field testing, which is certainly one of the most important part during the development process, in addition to it during the development and after the development, when we have concepts, we also validate them in our biomechanics lab. So this is what you can see basically here. We have, for example, here simulated lifting a load from the ground and putting it back up. We measured here the muscle activity in the back muscles in this case to really understand, does the concept provide the physical load reduction that it should be? And in this measurement, this is just one example out of many. You can see when lifting this load from the ground and putting it back down, we were able to reduce the average peak load of the back muscles by 40% and the average load by around 30%. So this basically also means it does not reduce the workload completely. It simply cuts off the peaks to a certain degree and makes every single repetition a little bit lighter. And this, of course, is then very helpful if you have to lift a couple hundred or 1,000 times per day. And this systems and other systems is now on the market, is being used across a variety of use cases. Just a couple of examples to give you an idea. Of course, we have airport baggage handling here, which honestly was not the biggest market over the last 2 years with Corona. There's a lot of things going on in logistics where you have the commissioning work, palletizing work, and so on. We have some work also in construction for the lift suit where you can see these rather forward-leaning tasks. emergency response services. Some of it is in agriculture. And of course, here my favorite use case here on the upper left corner is the horse smith using it to put shoes on its horse. And you can see here he needs to remain in this forward-leaning position for quite some time. And this is also where this kind of system can provide support and unloading. And with that being said, thank you very much for your time and attention.
Thank you, Dr. Bassenbach. We have now had a range of presentations showing, in fact, the broad perspective of exoskeleton, and we are now able to answer a question. We apologize for a little hiccup with Dr. Luigi, who had some technical problem with the presentation, but the video was supplying the information. So there are a couple of questions that are from the audience, and I will, although some of them were answered, I will ask them again, so then everybody can benefit. So all the participants can put their question in the chat, and Dr. Graf will collect them and then pass them to me or to the presenter in order to be addressed. So let me first present these two questions. One that is probably on the lips of everybody is the cost benefit. And that's certainly something that both the users and the companies may be of interest. So what is the benefit to the worker? What is the cost to the industry? Which was already approached by Professor Srinivasan as well. And the other question was a type of exoskeleton that would compensate for the disc height loss in spine. And so who is willing to address the first question, the cost-benefit analysis?
I can comment on it because I think this is a thought that many of our customers have in their head when they're talking to us. So I guess we see different motivations to invest at the moment in exoskeletons on a commercial thing. And I think Sasha mentioned it before, the long-term data is not yet available. And this is completely true. So the thought on can we, how many, the question is always how many sick days can it cut off our bill? I mean, depending on the country, on the social and the social security system or the health insurance system, this is what the companies cover themselves, right? At least for some days. And we very openly have to say that is something we do not know yet. This is the long-term data, especially for our systems that have only been on the market for a comparatively short amount of time. This data we do not have yet. But the motivation that, and we have seen a couple of motivations across the different talks, I think, the motivation for customers to invest in the technology is, we always describe it along the entire career of their workers. It would say, we have heard workers' retention, so making a job less strainful, making it less exhausting already can be a big plus for a worker. And if the worker has a better feeling in the evening, feels less fatigue, feels more fresh, then this has a certain value also for the employer who would pay for the exoskeleton, because this helps in workers' retention. This also helps in short-term retention. If the worker is not so, in many industries, it's very hard to find qualified people. And if they do not like the job and if they leave after a very short period of time, this causes high costs to the employer. And there we have customers who think about exoskeletons as a tool to make the job less exhausting, more pleasant, and therefore improve worker retention, short or long-term retention. This is certainly one motivation that we have seen before.
Thank you. Sasha, would you have any comments from the insurance perspective of, is there any incentive from insurances to promote or discourage the use of exoskeletons?
Well, not that we do have that here in Germany. And as Volker said, this is it's a very difficult question. First of all, it's an emerging technology, but to be honest, it's sometimes the same with ergonomic interventions, because that's always a very popular question. What's the return on investment? How long does it take to pay off? How do we measure that? Especially if it's not well, if it's safety, we don't have to discuss that. But if it's about well-being, so the answer is it depends. Probably people don't like this answer, and it's a common human factors answer. I have to say it depends on the use case, on the risks, on the type of tasks. You have to make a proper analysis. What kind of tasks do I have to solve? What are the risks? What are the challenges? What is my population? And is it a useful tool or not? So probably not a very helpful answer from my side, I have to say.
Divya, would you have a perspective from the user point of view? What do they gain? What do they lose in using the exoskeleton?
I think Sasha was spot on, because if you are talking about reducing musculoskeletal risks, it's not like you'll see the effect tomorrow, right? So if you're reducing the load on somebody by X%, you're talking about cumulative trauma and effects that you might offset in years and decades. So it's not sort of black and white that you implement an exoskeleton today, you compute the change in risk, and tomorrow you suddenly have a sort of change in disorder. So that I think is the challenge that anybody from an implementation perspective is also facing. Like, if the ergonomist on the floor might be super excited about the technology, but if they have to make this case to their own leadership, then they have these same hard questions to go through in terms of computing ROI. And I don't know of anybody that has solved it yet. These are questions we're all struggling with together. That's the hope there.
Yeah. But do the user think that they find a benefit when they start using it, or where they complain about some issues? Because effectively, as has been presented, there are a lot of exoskeleton, and effectively they have to be designed as a function of the task and the environment, as was presented lately. And also at the beginning, in how they fit. So do the workers perceive an immediate benefit, or do they are more reluctant to use them because of some reasons?
I think the question has slightly shifted now, but if we're talking user acceptance, that also is a complicated question. So I'll say my piece first, and then I think everybody will have something to say about this. There are certain tasks for which the exos are golden, right? They were designed to work for those tasks, and they do work for those tasks. In those questions, in those specific cases, effectiveness is not the main issue, but a worker has a zillion other reasons to not like the technology, even if it is effective. I mean, they feel hot, they feel constrained, they can't make the movements that they can normally make without thinking through them. So there are a variety of reasons that have nothing to do with effectiveness that are still coming in the way of, I think, a worker liking the technology and adopting it. And that was the perfect situation where the EXO was effective. And then we have all these other tasks that the EXO was not designed for. So the question then becomes, to what extent does an EXO have to be useful over a job, right? What if it helps only 15% of the job? Is it still then something you as a practitioner would recommend and I as the user would adopt? So it is a very complicated question, Bernard. Does anybody want to add to that?
I do.
Well, I would just follow up with that, Divya. It's, if it helps, 15% on one job, but then reduces your performance X% on another job, how do you balance between those two activities within the workplace? And then do you require the person to wear it some of the time and then not? And then you have inefficiencies from the time it takes to don and doff. So you'd really want the system to kind of not be affecting the other jobs if it's helping that one for that risk balance. So there's really kind of more of a full task analysis that needs to be performed for these systems in a real job environment, that right now we're looking at these exoskeletons kind of task by task and not in activity by job.
Now, Dan, you mentioned this active exoskeleton, and so we hear that effectively the task, the environment are extremely important. Is there any closeness to the universal type of exoskeleton that would be accepted for a very wide range of tasks, active or passive?
Yeah, unfortunately, we're still a long ways to getting the universal exoskeleton. Where we're going to see the biggest growth is in niche use. So you have an exoskeleton that's like a toolbox. If you're going to do a bunch of drilling and hammering, then you put on an exoskeleton that's specifically designed for that task, and you pull it out of the toolbox. we really don't have universal exoskeletons that are good for many, many different tasks. And I think this comes up over and over again in Leah's comment, right? Like you may help out one task 50%, but then you make it worse on other tasks by 15 or 20%. How do you balance that? And in the end of the day, it's going to be about comfort and productivity. And it's still a nascent field where we're going to make progress. But right now, an exoskeleton is going to be good at one thing, and that's pretty much it right now.
Thank you very much for all your comments. And
Hey,
now,
I just have one remark, which is also a classic, also not specific to exoskeleton, but I think is specifically in this area also very important from the human factors point, is worker participation. Also, we've seen that in the presentation from Volker, is involve the people, because this is really getting close to their body and they can give you an impression. It's tough to count that in numbers and in euros or in dollars or anything, but ask them. They give you feedback, they tell you, and believe them. If they say, this is not helping me during this half shift, during that job, believe them, because otherwise they are not going to use it. And it's it's close to the body. So people get more sensitive than using a lifting device, which they very often do not use. So then they even do not use this. So just a very quick remark, maybe helping a little, but also a standard answer, participation during implementation is crucial also for exoskeletons.
thank you very much. Now, to address the second question about this compensation of the disc, the loss of disc height, does any of you has a perspective on that, whether it would be an active or passive type of exoskeleton? If I understood the question properly.
I'm not entirely sure if I understand the question, but I would rather see there's a difference between a soft and a rigid exoskeleton, honestly, if I understand correctly. But I might be too stupid here.
Because the person was asking about the biomechanical issue and the torso lordosis that is changing due to the change in height of the disc. So is there any exoskeleton that is addressing a sort of rehabilitation issue, so to speak, or return to work with the use of an exoskeleton that would compensate for some of these biomechanical limitations?
Yeah, the best answer I would give you is we still need to make measurements. There's a lot we don't know about how different parts of the body are being affected by the exoskeleton use, and they're just not widespread enough that we have a lot of clinical data at this point.
Leah, when you mentioned the fit of exoskeleton and how the static versus dynamic fit, and you also present the perspective of the workload that is associated with the use of the exoskeleton. So in these situations, do you see that the fit could be acceptable at the beginning of the use and then dynamically change as a function of what people do, and due to the diverse type of tasks that they perform? Would the fit be strongly modified to be more an impediment after than at the beginning?
Yeah, so I think there's a lot to that question that I'm sure also a lot of other people in the room would like to talk about. But I think briefly, there's this aspect of initial sizing, right? How do you initially size the device for the person? And that can be done a lot of times in a static sense, where you just kind of stand and make sure different parts of the system are aligned appropriately. But what really happens is as you use the system and as you move,